from the University of Colorado Boulder. In Boulder, Erin conducted her graduate research at the U.S. National Oceanic and Atmospheric Administration, where she combined field observations and chemical box models to study the impacts of day and nighttime chemistry on U.S. urban air quality. Erin currently holds a postdoctoral fellowship at Dalhousie University in the Department of Physics and Atmospheric Science, where she is now using global chemical transfer modeling and collaborating with researchers in the Occupational and Environmental Health Division at UBC to study global sources of fine particulate matter and the associated burden of disease.
Great, thank you. I'm very excited to be here, so thanks for having me. As my title and intro suggested, I am actually an atmospheric chemist, atmospheric scientist by training, but I've had the fortune to work with Randall Martin at Dalhousie and Michael Brower here at UBC, who have really embodied the spirit of working across disciplines to address challenges related to air pollution. So today, I'm going to be talking about work that I've been doing over about the last year towards quantifying the disease burden associated with dominant sources of ambient fine particulate matter around the world. I'm going to start by providing a brief introduction to the topic and some motivation for this work. I'll spend most of my time talking about the methods I've been using, primarily global 3D chemical transport modeling, as well as developing a new emissions inventory. And then the last part of the talk will be focused on some of our preliminary results, sensitivities, and then connecting back to the health community. And I'd also like to thank, before I get started, my multiple co-authors, which are listed here, particularly Randall and Mike. Okay. So for this talk, I am defining ambient fine particulate matter as PM 2.5. So aerosols are gases or liquids suspended, solids or liquids suspended in the gas phase, and particulate matter, or PM 2.5, is any aerosol that has a diameter less than 2.5 microns, or micrometers. So to give you a sense for the scale of that, here's just an image from the EPA. So if you were to take a strand of your hair, about 20 or 30 of these PM 2.5 particles would fit across the diameter of that strand of hair. So we're talking about extremely small particles. And these are small enough that, well, when they're in high enough concentrations, they can scatter light and reduce visibility, like the background image that I'm showing here. But they can also make it past your nose hairs, down your throat, into your lungs, and cause respiratory diseases along with other health impacts. Just to give you a little bit of background about me, I spent the last 4 or 5 years working in a lab where we collected field measurements. So we developed these instruments like what's seen here, these field instruments that make very accurate measurements of aerosol precursors as well as aerosols themselves and the composition. We put these instruments onto mobile platforms like aircraft or ground sites, tall towers, for example, and using this data combined with very detailed chemical box models, I've been able to quantify some of the local and regional sources of wintertime air pollution. So that's a little bit of my background. But we know that particulate matter doesn't just exist, for example, in Salt Lake City, like the background image I'm showing here. Fine particulate matter is ubiquitous around the world. So here is an image of surface estimates of PM 2.5 globally. I'll talk a little bit more about this particular product later, but this was developed by Melanie Hammer in our group at Dalhousie. And based on this plot, we see that particulate matter does exist everywhere. And from an atmospheric science perspective, we atmospheric scientists think that particulate matter itself is interesting, inherently interesting. So that's one of the reasons why we study it. But another reason is because particulate matter impacts human health. And I think that's the motivation for this audience here. So the global burden of disease has actually combined high-resolution surface estimates of PM2.5 mass, like what I'm showing here, not this exact product, but like what I'm showing here. They've combined these with epidemiological models to actually estimate that fine particulate matter, or ambient PM, was responsible for about 5% of all deaths worldwide in 2017. So these are results from that global burden of disease study for their 2017 results, and I'm showing absolute number of deaths, and they're averaged over each country. But to put these numbers in perspective, I wanted to also show how particulate matter relates to other health risk factors. So if you look globally, these are the top 10 health risk factors from the 2017 GBD for all ages and all sexes. And particulate matter, which is highlighted here, is the fifth highest health risk factor globally, so contributes to about 60 deaths per 100,000. But you saw in the previous map that the absolute number of deaths and the absolute concentrations of PM2.5 vary around the world. Turns out the relative risk associated with ambient PM also changes depending on where you are. For instance, if you look at countries with a high socio-demographic index, particulate matter falls down to about the 10th highest risk factor, but for low socio-demographic index countries, particulate matter, now this is including ambient and indoor particulate matter, but particulate matter is the leading health risk factor. So it's really important that we address this issue. And the way that in our group we've decided to address this issue by trying to identify dominant sources of this particulate matter. So if the ultimate goal, another way to look at that is that if the ultimate goal is to reduce the mortality associated with PM2.5, we can represent that by this general expression here, which is related to the population PM2.5 exposure and the baseline mortality. Now, we don't have any control over baseline mortality rates or how the population may vary in different locations. What we do have control over, though, is this exposure part. So if we want to reduce mortality, we want to reduce exposure. And exposure itself can now be represented by this expression here, which is related to the relative risk associated with various concentrations of PM2.5. So these particular relative risk curves are from an epidemiological model, the integrated exposure response model. I'll talk a little bit more about this model later, but just to show you right now, I just wanted to show you what these curves looked like. But again, we don't have any control over how our bodies will respond to inhaling particulate matter, so the only thing that we actually have control over is this PM2.5 mass component. So if we want to reduce mortality, we need to reduce concentrations. How do we actually do that? Well, you can think maybe in theory a good approach would be to identify dominant sources of particulate matter. Seems like a first approach. But PM2.5 is a complex mixture. So I'm just showing here a globally averaged distribution of different components that actually make up what particulate matter is. So, for example, sorry, some of these are whited out. For example, you have these inorganic components such as nitrate, ammonium, and sulfate, as well as organics, also black carbon, sea salt, dust. So all of these different species make up what we're actually calling PM2.5. And these various components are related to sources. Particulate matter is formed from, or it's emitted directly from primary sources, such as you can almost see here. There's a cruise ship here emitting a lot of black carbon directly into the atmosphere. Wildfires emit a lot of direct particulate matter directly. But there's this added complication that particulate matter, especially the small particles, are formed chemically in the atmosphere from nonlinear chemical reactions. So just to give you one example, from the transportation sector, vehicle emissions, combustion emissions, you get a lot of emissions of nitrogen oxides, or NOx, if you've heard of those. It's a gas phase class of compounds. Similarly, agriculture, so cows, chickens, pigs, those all emit a lot of ammonia. So again, that's a gas phase compound. So you have these two different sources emitting these two different gaseous compounds. And in the atmosphere, those can combine and chemically form ammonium nitrate aerosol. So you have gases from different sources combining in fairly complex chemistry to form particulate matter. So this just gives you a sense for the fact that this chemistry isn't necessarily, the sources aren't necessarily that, it's not that easy to identify them. In addition, there's an added complication that the sources and the composition of PM2.5 varies around the world. And so I'm just showing some representative pie charts here of how the different species are expected to change in various locations. So how do we actually develop effective mitigation policies? Well, measurements are important, I would say, because you can get some sense for where the aerosol is coming from based on the composition. For instance, if you have a lot of these inorganic compounds, that might indicate that you have dominant sources of transportation or energy production, for example. But a lot of these sources also have, or a lot of these components also have multiple sources. For example, organics can come from natural sources, but also human emissions. So measurements are one component that are very important, but they don't answer everything. They can't capture some of the chemical complexity that I was just mentioning with the ammonium nitrate aerosols. And also long-term measurements that we need to connect to chronic exposure estimates, those don't actually exist in most of the locations around the world. So this is a figure from Randall Martin's recent 2019 paper where the colors are indicating the number of air quality or PM2.5 monitors that exist in a country per million people. So you can really see that Canada is really one of the only countries that has even close to 10 monitors per million people. So in a lot of these regions around the world, we actually don't know what the PM2.5 mass is. We don't have that measurement, and we don't know its composition. So how do we design effective policies for those locations where we don't have any measurement information? So our approach has been to use chemical transport modeling to fill in some of those gaps. So the idea is that you can develop a simulation that represents the composition of the atmosphere, and once you identify or evaluate your base case scenario, which I'll talk about in a few minutes, once you develop your base case, you can start playing with the emission inputs in your model. So for example, you could remove transportation emissions and see how that changes the particulate matter concentrations. And because we're using chemical transport modeling, changing or removing certain chemical species will have an impact on the chemistry. But because we're modeling the chemistry, we have a more accurate representation of what's going to happen to the aerosol in the end. So I'm not the first one to do this type of work. I just wanted to highlight two projects that have been done as part of the GBD MAPS projects that Michael Brower and Randall Martin have been a part of. So the left is showing source contributions in India for 2015 simulations. So you can see the number of deaths associated with these different sectors. And then the middle plot is showing just a representative result from 2013 simulations over China, where they were able to quantify the number of deaths associated with PM2.5 that originates from coal combustion. And then in Randall's group, Crystal Weigel, who's now a postdoc with Randall, also looked at source sensitivity simulations on a global scale. And so the pie chart on the right is showing the globally averaged contributions from these different emission sectors. So you can see that residential, sorry this is cut off, but let's see if we can. Okay. So residential emissions are the largest contributor, as well as industry and power generation. So at this point, we have these examples of using this method to address this question of what are the dominant sources and what are the associated health impacts. But now for my work, I want to expand this to a global scale, but for a contemporary simulation. So you'll notice that all of these studies are for 2013 through 2015. There have been changes in emission efficiency standards as well as aggressive emission regulations in China recently, and some of this work won't necessarily capture those recent changes. So we want a more contemporary simulation to get a sense for what's happening today. We also want to identify or break down some of these sectors into finer sectoral resolution. For example, for power generation, from a policy perspective, it is a lot easier or feasible to develop policies for coal-fired power plants, for example, instead of targeting the entire sector of power generation. So that's what motivates my work, where for effective policies, we need to identify the dominant sources at the national level for all world countries. Thank you. And to do that, we need a contemporary simulation of PM2.5 concentrations that has a globally consistent definition of sectors across the world, and then more detailed sectoral information. Okay, I mentioned that the way I'm doing this is using chemical transport modeling, so I thought I'd spend just a minute or two talking about the actual model that we're using. Randall's group uses the GeosChem model. It's a 3D global chemical transport model that uses assimilated meteorology from the NASA GEOS-5 model. So what that means is that we're taking meteorological fields such as cloud fractions or temperature and relative humidity. We're taking those from a NASA model and then putting them into a model that simulates the chemistry. So the atmosphere is a fairly complex place. This is just a little schematic that I've drawn of some of the major processes that happen in the atmosphere. There's definitely more going on than what I'm showing here. But for example, you have your emissions, both natural and anthropogenic. You have gas phase reactions. You can have interactions between gases and aerosols. Your aerosols can transform chemically. You can have exchange with the surface or with the ocean. You have wet deposition, where you have rain pulling out chemical compounds from the atmosphere. Cloud processes transport. These are just some of the big things that we try to represent in these models. So what we're actually doing is using algorithms to represent both the physical and chemical processes occurring here. To put that in mathematical terms, what we're actually doing is solving the continuity equation for every species I. So we want to solve for the concentration at all time steps, accounting for transport due to advection, and then any production and loss processes that are associated with emission, chemistry, and deposition. But of course, we're not calculating the concentration for each species on a global, or we're not calculating one number for the global atmosphere. We are doing this calculation in a series of grid boxes. So we grid the world. In my simulations, I have about 91 by 144 horizontal grid boxes, 47 vertical layers. And GeosChem itself is representing or calculating concentrations for 219 species, and it includes about 645 chemical reactions. And that might sound like a lot to you. I've run much simpler chemical box models before that have included over 15,000 chemical reactions, and that doesn't even include everything that's happening in the atmosphere. So there is a lot of atmospheric chemistry that's going on, and what large-scale 3D models like this do is that they try to lump all of that chemistry into representative reactions because we don't have the computational power to represent all of that chemistry. So we're breaking that down or simplifying it into the most representative reactions and species. Okay, so when you actually run the model, now I'm showing you what my initial simulation looks like. And as I mentioned before, you want to evaluate your base case simulation because ultimately if you trust your model, if you trust your base case, then you can start to play with the emission inputs. So on the top figure, I'm showing you all of the available annual average measurements of PM2.5 mass. So this might look odd to you in the fact that there are only measurements really in North America, Europe, China, and India, and that is one of the limitations that we have currently. Randall Martin is heading a project called Spartan Network, where the idea is to set up more monitoring locations in some of these undersampled locations. But right now, for 2017, these are the measurements that we have to compare to. So then on the bottom, I'm showing the default simulation. You can see generally the trends work out where you have lowest concentrations over North America, highest concentrations over China and India. But if you look at the correlation between the model on the y-axis and the observations on the x-axis, you can see that there's a positive bias in the model. So the points here are colored by region. So the positive bias is being driven by a lot of these high concentrations in China and India. But we overall have a 23% high bias. And just looking at total PM2.5 mass, we're not really going to be able to determine why we have this bias. And again, we want to work to be able to trust our model so that we can then have faith or confidence, I should say, in our emission sensitivity simulations. So this is where an atmospheric chemistry or atmospheric science background comes in, because we can actually look at locations where we had composition measurements to try to determine why the model is over-predicting the mass in terms of which species it's over-predicting. Then we can dig into the chemistry and try to tweak that and create a more accurate representation of the ambient environment. So this figure here, I'm showing the normalized mean bias in the simulation versus the observations. So and these are for all of the various components that make up PM2.5. So a positive number means that the model is over-predicting that component relative to the observations. You'll see here that we have a positive bias in dust, but that's a relatively small portion of the total PM2.5 mass. What's more concerning is this nearly 250% bias in both nitrate and ammonium. So we have this over-prediction in ammonium nitrate aerosol. I mentioned this a little bit earlier in the talk. So the first thing we need to do is check our measurements. I think it's always a good reminder that measurements, regardless if you are making them or not, are not necessarily telling you what the true concentration is. And so just to give you one example for ammonium nitrate, there's a long history with measurements of ammonium nitrate aerosol, where historically measurements of total mass and composition have been made on Teflon filters. So the idea is that you have a Teflon filter, you're pulling air, ambient air, over the filter, and you're collecting the aerosol mass on that filter. However, ammonium nitrate is well known to evaporate off of Teflon filters. So what that means, and what this plot on the left is showing, is that if you sample on Teflon, you are losing up to 60% of your ammonium nitrate on that filter. Now that's relative to if you measure on nylon. So a nylon filter ammonium nitrate will stick, it will not be resuspended. So this is just one example of checking your measurements and trying to dig into whatever metadata that you can find to make sure that you have confidence in the data that you're actually comparing to. And so that's what I've done for this work. I've gone through and checked all the ammonium nitrate measurements. I have the most confidence that I can have in those measurements, which means that this 250% bias is not being driven by the measurements. I think it is being driven by something in the model. So now we need to dig into the atmospheric chemistry that's happening in the model. So a little bit of chemistry, although I've already talked about this reaction. So you have ammonia that's directly emitted from agriculture reacting with now nitric acid, which forms when you have NOx emissions, for example, from combustion that are oxidized in the atmosphere to form nitric acid. Those two molecules combine to form particulate matter, ammonium nitrate. Now, from an atmospheric chemistry perspective, we typically think that nitric acid is formed from this daytime reaction between NO2 and the OH radical, but there's also an important source from nighttime chemistry that involves N2O5. I spent 3 years of my PhD on that chemistry, so I won't go into too many details here, But basically you have emissions of NOx that end up being oxidized to form NO3 and NO2. They form N2O5 at night. N2O5 can then react with aerosol particles to form nitric acid. That nitric acid, of course, can go on to further form ammonium nitrate. So the atmospheric fate of this compound, N2O5, is important because it can persist over the course of the night, and it will contribute to, for example, ozone pollution the following day. But if it does react with particulate matter to form nitric acid, that can impact your overall aerosol budget. So the fate of N2O5 is represented or can be predicted by this one parameter here, this uptake coefficient. And in the default version of GeosChem, I won't go into the details here, but in GeosChem, you represent or you calculate this parameter, gamma, by doing the calculation on different aerosol types. So in the model, you're assuming organics are a separate aerosol type from dust and sea salt, black carbon, and then your sulfate, ammonium, and nitrate are a separate aerosol type. And then this is globally what you would get for that uptake coefficient using this default method. Now what I've done is change this calculation. So now I represent uptake as an organic coating around an inorganic aerosol core. And the reason that I've done this update is because based on my previous field measurements and box modeling, I've been able to determine by looking at 16 to 20 different parameterizations that this form representing the chemistry and the aerosol physics in this way is the best or the most accurate representation of this N2O5 uptake coefficient. So not sure why the figure isn't showing up there, but the takeaway here is that when you make this change based on very detailed atmospheric chemistry studies that, I'm not talking about in detail, based on these changes you get a decrease in your uptake coefficient, which means you have less conversion to nitric acid, and the end result is that you'll have a decrease in your aerosol nitrate. So this is just one example of some of the work the detailed chemical and physical work that goes into accurately representing the ambient atmosphere in GeosChem. GeosChem itself has a community of hundreds of researchers like myself who are working on different processes that are just as detailed as this, and we really want to try to represent the atmosphere as accurately as possible. So this decrease in nitrate helps with, I end up improving the that's fine, yeah, thanks, okay. So I end up reducing the bias in ammonium nitrate, significantly reducing the bias, and that ends up improving the agreement. So if we were to look at a correlation plot between the updated model with the observations, the correlation was better than the default model. So we had an overall bias of negative 12% relative to our overall bias of 23% originally. So we improved the bias, and the slope is closer to 1 compared to the default, and our R value is higher. So basically the conclusion of the slide that's not showing is that I made...
It's showing online.
Okay,
Yes.
okay, great. Okay. Well, I made all of those changes. I improved the base case scenario. It now more accurately represents what we actually saw in our observations, which means that we can now trust our model enough to conduct these emission sensitivity simulations. So moving on to actually how we do those sensitivity simulations, I'm going to end up calculating the absolute contribution to PM2.5 from each emission source by comparing our base simulation to simulations where we remove different emission sectors, and this will calculate the fractional contribution, and then multiply the fractional contribution by the satellite-derived high-resolution PM2.5 product. And this is what I showed at on one of the intro slides. And so this high-resolution product on the right I won't go into the details, but essentially it uses satellite retrievals that are at high resolution, combined with geochem modeling, combined with surface observations to develop a map of PM2.5 surface concentrations at either 10 by 10 kilometer resolution or even 1 by 1 kilometer resolution. And so the reason I'm using this method by calculating the fractional contribution, multiplying it by the satellite-derived product, is because the native resolution of the model is 2 by 2.5 degrees, which is around 200 kilometers by nearly 300 kilometers. So to be more relevant to health studies, we want to get down to a finer resolution. So we're calculating fractional at the native model resolution, multiplying it by the high resolution satellite-derived product, and that's how we're going to get high resolution estimates of PM2.5 mass. So I showed you a base case simulation, and I was supposed to show you that the agreement was improved, but there's an important component of the simulation that I haven't talked about yet, and that's actually the emissions. And the more confidence that we have in the emissions, the more confidence we have in our sensitivity simulations and our absolute concentrations at the end. So again, to remind you, we want a contemporary simulation that has global consistency in its sectoral definitions and then fine sectoral resolution. So this is an area where I think we've struggled with as an atmospheric science community in the past, because we are dependent on these large-scale emission inventories that are frequently developed by groups, and it's all kind of done behind the scenes. It's a bit of a black box, and they end up producing these great gridded emission products, but you don't necessarily know everything that went into the calculation of the emissions, and you can't get into the system to control or change the calculations in any way. However, that all changed last year when a group at PNNL, so Pacific Northwest National Laboratory, headed by Steve Smith, when they developed this community emissions data system. And so what this is a series of R scripts that you can go into GitHub and download today, and you can actually run the system yourself to produce these emission inventory files that are gridded at 0.5 by 0.5 degrees resolution, and it provides information for all of these various species for a series of different emission sectors and fuel types. Some updates that I've made to the system are to improve or calculate more recent years of emissions. So the original SEDS inventory that was discussed in Rachel Hosley's 2018 GMD paper, those emissions only went out to 2014. I've actually been able to get into the system and make some updates so that we can get emissions out to 2017 so that we have a more contemporary simulation. I think it is important to understand some of the details and some of the complexity that goes into these calculations. So I just wanted to give you an overview with how SEDS generally works. There are three main steps that I'm going to walk through. The first is the calculation of the default emission estimates. Emissions are calculated as a function of activity A times emission factor. And SEDS is doing this calculation for nearly 195 countries and regions, 54 different emission sectors, 9 fuel types for this entire time series, and then for 9 different species. So this is an incredible amount of information. The activity information, this is, for example, fuel combustion. And so this information comes from products that are produced by the International Energy Agency, or BP, and so they tell us how much fuel is consumed by different sectors in different countries each year. And then the emission factors tell you how, essentially the concentrations of the species that are emitted per unit of fuel consumption. And these emission factors come from other models such as the Edgar model and inventory. The second step is to scale the emissions. So the philosophy of SEDS is that it does the best job that it can to calculate emissions on a global scale using consistent methodology, but it recognizes that there are many other regional inventories, for example, the NEI over the US, that do a better job of calculating their national level emissions. So SEDS does a good job of trying to get a global, consistent picture, but recognizes that these regional or more authoritative inventories likely have more accurate information. So what SEDS does is then takes the regional inventories and the default emission estimates and calculates a scale factor for the years where there's overlapping data. But a lot of these inventories aren't necessarily available to the most recent year. Most of them stop in 2017. Some of them stop in 2012, for instance. So you can calculate these scale factors for years where you have overlapping data, and then you can either extend forwards and backwards for years that you don't have overlapping data. And this is a map of just showing that every world country is scaled to one inventory or another. I don't want you to read all of these. I just wanted to highlight that there are two updates that I made where I'm now scaling Africa, all African countries, to the DICE Africa emission inventory, and then I'm scaling India to new 2015 emissions that were produced by our collaborators at IIT Bombay. So these are two updates that I've made. And then the final step is to actually spatially grid these emissions, because at this point all of these calculations have been done for national totals, country totals, but we want to know where the emissions are actually occurring so that we can put that into the geochem chemical transport model and understand spatially how our emissions are distributed and affecting PM 2.5. So we'll just continue on. So all of the sectors in the black are what SEDS ends up producing if you were to download it and run it today. But because it is a emission system, I've gone in and pulled out additional information. So everything in red are all the updates I've made. So for example, I was able to split the transportation sector into road emissions versus non-road emissions. I've split residential, commercial, and other into various sectors. And then the really unique aspect, I think, is that we've pulled out different fuel types. So I now can examine coal combustion associated with all of these different sectors, as well as biofuel, and then all of the remaining fuel types, which are primarily liquid fuels. So combined, SEDS plus the geochem model can give us a contemporary, at least 2017, most contemporary simulation we can get with a global consistency in sectoral definition, and then finer sectoral and fuel type resolution. Okay, what do these emissions actually look like? So if you put them into geochem, these are now showing the 2017 global averages for emissions for these different chemical compounds. These colored bars are the SEDS emissions, and they're colored by the fractional contribution from these different sectors. And then the light gray bars are indicating all of the other emissions that are included in geochem, including open burning, so fires, as well as other natural sources. And then we can compare these SEDS emissions to the most recent global inventory that was produced by Edgar. These emissions the Edgar emissions were released a few months ago, and they only go out to 2012, whereas SEDS are showing 2017 emissions. But you can see generally good agreement between the global totals between SEDS and Edgar. One exception is SO2, and this is actually because there have been large global reductions in SO2 emissions between 2012 and 2017. So that's why you see that difference. But the really novel aspect of SEDS is that you can get this fuel type information that I mentioned before. So now I'm showing the same plot, the colors are the same, but now the hatching is showing the fuel type contribution. So just to show you highlight three examples. For NOx emissions, the largest contributing sector are road emissions. Those road emissions are primarily from oil and gas fuel type. And if we look at the spatial distribution, you can see that the NO2 road emissions in SEDS highlight some features that you would expect. For example, you can start to see some individual roads in North America as well as Asia. Next, for SO2, Energy production is the largest contributing sector, and a large component of that is from coal combustion, which is shown by this pie wedge here. And then if I plot the spatial distribution of coal energy emissions, you can see that they're point sources. So these are representing individual power stations or power plants around the world. And then the last one that I'll show you is organic carbon emissions. The largest sector, largest contributing sector is the residential sector, and those are primarily from biofuel types. And so then again, if we plot the biofuel emissions from this one sector, you can see that there are a few locations around the world that are highlighted, particularly in India. So this just gives you a sense, hopefully, of the rich information and data set that we actually have from this inventory. Okay, so now to some final results. You guys have been waiting patiently. Just as a reminder, I'm calculating total contributions as the base simulation minus these sensitivity simulations to get a fractional contribution. That's what I'm showing in this plot here. So the color scale is going from a 0 to 50% contribution to total PM2.5 mass. I am multiplying that by the satellite-derived product to then get high-resolution estimates of the absolute contribution. So I'm just showing the example for agriculture here. Of course, I have this information for all the different sectors. So just to give you a sense for what some of the results look like, again, I'm showing agriculture. These are the aggregated sectors, so residential, commercial, and other, total transportation, industry, energy, and then total dust. So this is including natural dust as well as anthropogenic dust. And so there are a few trends that kind of fall out here. You can see India and China really have large contributions from all of these different sectors. And then, of course, you have large dust contributions in Africa. And then I think one of the most novel aspects of this work is that we've been able to provide the first global estimate of PM2.5 contributions from both biofuel and coal. And so these are highlighting those initial results, where again you can see both in coal and biofuel you have large contributions over India, you have large biofuel contributions over Africa, and then both have large contributions from China, in China. Okay, so the slides that are not showing up, what I was going to show you was instead of looking at the individual sectors, you can actually compare the contributions from different sectors in different countries around the world to kind of pull out what the dominant sector is in each country. And the takeaway there was that similar to previous studies that have looked at these large aggregate sectors, you see dominant contributions in a lot of locations from residential emissions, as well as energy production and industry, as well as agriculture in some particular locations around the world. There is a detail about nonlinear chemistry that I'll just maybe not talk through if the slides aren't going to show up. Okay, so basically the takeaway from those sections is that we can identify contributions, we can identify concentrations of PM2.5 from individual emission sectors and fuel types. That was the takeaway of the work that I've done. The next steps, which I haven't quite done because the global model simulations just finished earlier this week. So the next steps will be to take those PM2.5 mass concentrations from all of those different sectors for all countries around the world and then relate them to excess mortality using these relative risk curves. So I showed these at the very beginning. These particular curves for various diseases are from the integrated exposure response model. This is what's actually used or was used in the 2017 GBD. It includes risk information from outdoor particulate matter as well as secondhand smoke and active smoking. But then there's a second model that has been published last year in PNAS by Richard Burnett. And so this GEM model, now I'm showing those relative risk curves here in the dashed lines. And these give a very different result in terms of the relative risk at a given concentration of PM2.5. And the difference here is that these new curves have been developed from a model that incorporates 41 cohort studies and only accounts for risk associated with outdoor air pollution. And when you look at a global scale, you get about a 20% increase in mortality globally when you use the GEM model relative to the IER. So our plan is to kind of bound the possible excess or possible number of deaths or excess mortality by calculating the source contributions using both of these curves. With the intent, of course, of conducting simulations similar or work similar to what I showed you before, where we can quantify the number of deaths associated with all of these different sectors and fuel types, as was done in India, but now doing this globally for all 195 world countries. So just to quickly conclude, I talked about how PM2.5 is ubiquitous, and to reduce the number of mortalities, we need to reduce exposure and concentrations. Therefore, we need to identify dominant sources. I ran the geochem simulation. This is a figure that didn't end up showing up. Or you can see the updated model in the dark bars has an improvement relative to the initial model, which is shown in the light bars. So we have a trusted base case simulation. I've implemented, or I talked about the SEDS emissions that provides more contemporary information as well as additional fuel types and sectors. And this is one of the figures that didn't show up. So this is showing the dominant sector that's contributing to PM2.5 on a national average for the world. So you can see that large contributions, for example, energy and agriculture, as well as natural dust in a lot of the world. This is a pie chart of the global distribution of source contributions on a population-weighted average. So, like I said before, residential emissions are dominant, as well as industry and energy. And then finally, what we want to do is combine these absolute source contributions with epidemiological models to quantify the excess mortality associated with each of these sources for each country around the world. So I will take any questions. Thanks.
Thank you so much, and I would like to deeply apologize for all of the issues that you went through. We will figure that out. However, thank you. You were wonderful in coping with everything. So we still have 10 minutes to take questions for this talk that was presented. There's no need to repeat the questions.
Okay.
I will monitor the online audience, and
Hi. I have a question about the excess in the ammonia. Was that when you updated the chemistry for the to essentially reduce the yield of converting the N2O5 into HNO3? Did that just effectively, is that like a limiting factor in the reaction so that you weren't using as much ammonium nitrate, that the influence of ammonia was also reduced, or was it something else for the ammonia?
Yeah, so that was part of it. And then actually the factor that had the largest impact was changing the scheme for the wet deposition. And so that's the amount of compounds that are taken out of the air when it rains, for example. And so that won't just affect nitrate, that will affect other species as well. So that actually had the largest effect of all the changes I implemented.
Are you trying to prioritize online? You want to look very good. Hi. I was also impressed by your and I have a couple questions that are pretty high level and I need all that, but that's okay. So where the biofuels seem to contribute more in India than China, which is like graphically it looked pretty dramatic. This is maybe just knowledge translation about that. Is that because China's developed so much more in terms of not just burning biofuels? Like by that I take it you're talking about like stoves and like wood at home and that kind of nasty stuff. Is that what that reflects? Yeah, from the left.
Yeah.
Because China's going to jump ahead of India in terms of that stuff.
Yeah, I think that's correct. Yeah, I will say these results are a few days old, so I still have to dig into some of the details. But the biofuel contributions are primarily from residential, the residential sector. So the difference in China and India, there will be some influence of industry emissions, but primarily the difference is driven by the residential sector, which will have to do with the stove emissions like you've been mentioning. Yeah.
And then sort of another similarly high level with, because that would be a graphical stuff, is, evocative.
Yeah.
Towards the end, the one that you didn't show, but then you showed at the very end.
Yeah.
It looked like Canada was more similar to Europe, just by that color coding, and I just didn't know if that was, it was just kind of like, oh, Canada looks more like than the U.S., which is our southern
Yeah.
and all that. Should we be making much out of that?
No. No. Yeah. So I also showed a bar chart that provided more quantitative information about the sector breakdown. So this is just showing relative to the other sectors in that country on a country population weighted average. Agriculture, for example, in Canada was the dominant sector, but in terms of absolute concentrations, you do see a lot of similarities between Canada and the U.S. So yeah, don't read too much into that plot.
I won't call them media, just
Yeah, no, please don't.
I have a question for you.
Yeah.
That's okay. So in the beginning, you were explaining how you went from your boxes to modeling boxes into doing a group.
Yeah.
And explaining that you had to simplify it in terms of the layers that you were choosing. So thinking exposure, thinking models that we need to have in accurate exposure because you want to put that into the final equation as a burden.
Yeah.
How do you go about trade-off in terms of choosing the number of layers and replicating what's happening and getting a good estimate versus having the minimal amount of layers to be able to have the largest possible estimation? So how do you go about that decision?
Okay, so I think if I'm understanding your question correctly, you're asking about the vertical layers that we're simulating?
Yes.
Yeah. So that was just meant to show you that Geochem does calculate concentrations throughout the entire atmosphere, but all of the results that I'm showing are just from the surface layer. So you do have transport of chemical compounds from the surface up through the atmosphere through different boxes that represent the vertical distribution of the atmosphere, but the concentrations that I'm showing are just the surface layer, so the lowest box. And the reason that I'm using the lowest layer is because that's what's actually at the surface and that's what we are exposed to. So, yeah.
Thank you. Please join me in thanking this very fascinating and kind of complex but completely amazing talk. And again, apologies for the technical difficulties. Thank you very much.